Hi everyone, welcome everybody. Good morning, good afternoon, and good evening, depending on the time zone. This is Daniel, and this is the Zero Knowledge Learning Group. What we have here. The today's topic is the basics of circum programming, and this is like a series well organized by Linux Foundation Decentralized Trust, and then it's done by me. Actually, I'm like open source contributor practically in this project. So let me start with a little bit like logistics, how this whole learning group looks like. So it looks like this is a zero knowledge learning group. It's I mean, nothing special. What we technically do, we do like one meetup in each month throughout this year. It's usually the third Thursday. For some reasons, this Thursday is the fourth Thursday, but generally we try to do it in every Thursday throughout this year, or at least until the end of this year. Always from 6 o'clock Central European time. That should be like usually like 9 o'clock Pacific, if I'm not mistaken. So it's generally, yeah, good for a broader audience. The structure looks that way. We're gonna have like 1 hour practically each month. This is usually like a presentation, and sometimes we have time for a short discussion. But sometimes there's no much time for discussion. So I would encourage everybody, if you have like questions that I can answer during this call, or questions, I mean generally that that come up after this presentation or after this meetup, I would encourage you to use it like a Discord channel, which is gonna cover in a second. So generally, I would expect that there can be like practically a big discussion simply in a chat and not necessary in this meetup. We're gonna cover different topics on zero knowledge proof, mostly from a software developer or application developer's perspective, with some theory. So generally, I'm not a mathematician. I covered a few like meetups and presentations, plunging a little bit into the mathematical deeps or depths of zero knowledge proofs, but generally I'm not a mathematician. I'm more like an application developer. So I'm gonna cover more topics from an application developer's perspective. So again, but we had some theory. So the coordination is generally on the Discord of Linux Foundation Decentralized Trust. It looks that way. So if you are not a member of the Linux Foundation Decentralized Trust Discord channel, you can just Google it and you can find an invitation link for that. So generally, you will find it. If you're a member of the Linux Foundation Decentralized Trust Discord channel, then you're gonna find us under there's somewhere here like community, and we are at the end of these communities. So we got like zero knowledge learning group at the end of these communities. And again, so I mean, we just limit each of these sessions to 1 hour, and sometimes it's just enough for the presentation itself. So I would encourage everybody to use this Discord channel, and then basically, if you have any questions that I can't answer, for instance, during this call or after the call, I mean, just feel free to chat. Just feel free to join the channel and feel free to chat basically. So that's generally the coordination for this learning group. We're gonna have meetups. It's organized on meetup.com as usual. There's like a Linux Foundation Decentralized Trust meetup series, practically, I mean, for each countries. And then as basically this is like a more global meetup, then it is shared in practically each and every region. So basically you will find these learning groups overall. And we are having one repository as well. It's at the moment under my GitHub repo that practically collects all the information that we just share here. So you find here all the previous meetups, all the previous slides, all the previous recordings. And up to this point, we did not have much code because we covered more like a theoretical basis. But from this point, we're gonna have some code as well, and you will find the code examples here in this repo as well. Again, at the moment, it's in my repository. You will find it on the slides. But we have just created practically a Linux Foundation Decentralized Trust lab. And then this repo will be migrated to the Linux Foundation Decentralized Trust lab. And then basically you will find all of the materials there. So that's the idea. Again, we plan it at least till the end of the years. There are sometimes like quizzes and small programming challenges, and hopefully we can get some Linux Foundation Decentralized Trust merch at the end. I mean, for those who are, very keen on like solving programming challenges and quizzes. The second part of the logistics, that's like the year agenda. So we started somehow in February with some definitions and building blocks. We covered polynomial commitments in March. In April, interactive oracle proofs. We just start with programming with circom. So we're gonna have like a basic presentation or basics of circom today, and we're gonna have like a more in-depth presentation for circum in June. Then in July and August, we just blank cover Noir. That's again a zero-knowledge programming language. And from September till the end of the year, we just plan to cover like application development. So we cover like different topics. We just gonna cover like off-chain transactions, proving solvency or proving so generally like proving solvency of an exchange or something with zero-knowledge proofs. We just gonna cover roll-ups probably, and then in December we will have like a wrap-up on probably mention some more applications. So that's the idea for the year. So we are in May. We just start with programming with circum. Anyway, anything is just subject to change. So if you have like ideas that you want to push in, or you would like to just hear about it, then just feel free to use the Discord channel and feel free to give me ideas. I wouldn't say that I can prepare anything, but I mean if I have like the capacity for that, then you might suggest a different programming language than Noir, for instance. Although Noir is pretty popular at the moment, but if you feel like having some different zero-knowledge language, then we can take a look actually. Or similarly, if you have like if you're interested in like taking a look again just on a global level for another application, it's like not just off-chain transactions or roll-ups, but something else, then just feel free to have this idea in the chat, and then I can take a look if I can prepare that topic in a meaningful presentation in 1 hour. Again, I'm not a mathematician, I'm more like an application developer. So if you just want to hear from me very in-depth mathematics, then that's probably not me. So the agenda for today, we just gonna start with like summarizing ZK SNARK, and then we just gonna cover like zero-knowledge programming a little bit, having like core algorithmic considerations, domain-specific languages and tools for zero-knowledge programming. We just take a look on circum. I just prepared the demonstration as well, a code demonstration. So we're gonna have some demo and some code, and at the end I just defined a challenge. If you have the time, just you can likely like solve this challenge. And at the end we have like some links, resources and literatures. And if there's time at the end, then we can just have like a brief questions and answers, Q&A. Again, so generally I would say the general communication is rather in Discord. So if you have questions and answers, probably I can or we can answer these questions more in details in the chat. So let us start basically, and let me start with like ZK SNARK. So it's gonna be a one-slide summary practically on all the theoretical parts that we covered in the last 3 sessions. So if you think of like zero-knowledge SNARK or ZK SNARK, we usually have a model. We have like 2 actors. We have a prover and we have a verifier. And basically the prover tries to prove something cryptographically, and the verifier, I mean, should believe in this proof. I mean, should accept or reject this proof. And then the point is for this proof that basically it should have like a few properties. It should be like small and easy to verify practically. So that's the model what we have. So for going more into the details, we usually have a problem that we try to somehow express in this prover and verifier model. One example is like the Alibaba cave, if you still remember, or practical example is like finding Waldo or Wally on a picture. But we can have something different as well, like the prover might try to prove that she knows the preimage of a hash function and tries to prove it without practically, I mean, convincing the verifier that the prover that she really has the preimage of a hash function without showing this preimage to a verifier. That's like a more theoretical example. So to express this problem, this domain problem, we usually say we have something which is a computation. And the computation is pretty tricky. It's usually mathematical. We usually define problems with like arithmetic circuits, which has like plus and multiplication gates practically and inputs. And we have like X public inputs. We have W private inputs. We can say that that's witness. And then usually what we have, so again, so we have this arithmetic circuit somewhere, but usually we start with like a high-level computation, which is compiled to an arithmetic circuit, which is compiled to polynomials. And then basically these all of the zero-knowledge properties come from different properties of these polynomials. Again, different deep mathematical properties of different polynomials. We don't just have these 2 roles, just the provers and the verifiers, but prover and verifiers are usually like algorithms. So to defining things a little bit more in depth, we have like a prover algorithm. The prover algorithm takes like generally the inputs. So we have like the public input and the private input. We usually have kind of a pre-processing step, which is carried out before the proving and the verification. And the prover simply creates a proof based on this public input and private input, and then this pre-processing step. So again, just having this example, if we want to prove that we know a preimage of a hash function, then practically there's usually some pre-processing, but we have the public input, which we don't have at the moment, but we have just the private input, which is like the preimage of the hash function, and then based on that, we just create a proof. And we have a verifier as well, and the verifier is an algorithm as well. So it simply creates the public input, if there's any, the proof, and again, there's usually like a pre-processing step. So this is like a parameter for a pre-processing steps, and it either accepts or rejects this proof. So again, if we have like the example of a preimage of a hash function, then there's no public input. So we just take the proof, some pre-processing steps, and we either accept or reject that the prover really knows like the preimage of a hash function. And this whole structure has a few properties. So that's like that's the reason for SNARK, or that's the abbreviation for SNARK. So it's succinct. Succinct means that the proof is small. Complete means that if the prover knows really like a witness, then practically you can create a proof, and the proof will be accepted by the verifier. It is knowledge sound. That's the other direction. So if the verifier accepts a proof, then there's really a prover and the witness, and the prover really knows this witness practically, based on was the proof created, and that's what was accepted by the verifier. And we got one property, which is the zero knowledge property, which means that based on the proof and verification, nothing is revealed from this private input from DW. Usually zero knowledge is not necessary. So we have like a lot of applications where we don't have zero knowledge. For instance, in rollups, we don't need zero knowledge. We just need the succinct practically argument. And again, it's succinct. We have like non-interactive. Non-interactive means that we like this proof in one step. So we just don't like to be iterated very much. We just create a proof. The proof is either accepted or rejected. We just don't like too much or too many interactions between the prover and verifier. And the argument is knowledge is basically that the prover knows kind of a fact that will be accepted eventually by the verifier. So that's ZK SNARK. And then let's just take a look on the zero knowledge engineering flow. So usually, again, the core idea is we define problems with like arithmetic circuits, but practically nobody likes, programming arithmetic circuits or doing anything with arithmetic circuits. So usually what we usually have like a higher level language for expressing our problems, for expressing our domain. So usually we start with a higher level language for SNARK or ZK SNARK, and that's compiled to arithmetic circuits, and that's compiled to polynomials eventually. And based on the polynomials, we get the zero knowledge properties. But if we have like one general framework for zero knowledge programming, we just don't need to care about it because we have like one platform that creates everything for us. So as a programmer, what we do, we just have this higher level language. Again, it's gonna be circum, it can be Noir, but it can be like Socrates, Leo, Cairo, and so on and so forth. We just compile it to a so-called zero friendly format that can be like arithmetic circuits, or that's going to be like rank 1 constraints, and so on and so forth, which is somehow interpreted as polynomials. And then we get practically a prover and a verifier. And then based on this prover and verifier, we can create our proofs. But the point is that, practically as a developer, we just more or less, we just care basically defining our problem with this like higher level language. And all of the details or most of the details are hidden with the framework, with the platform. So, one question is it possible to do like zero knowledge and SNARK programming without cryptographic knowledge? That's gonna be somewhere the idea on the long run. It's still not possible. So, you still need to, most of the problems that you express with zero knowledge programming are more or less like cryptographic. So it's not absolutely without cryptographic knowledge, but basically you just don't need to care about a lot of details like, rank 1 constraints or proving algorithms and so on and so forth. So generally, we having like complex frameworks that can compile, test, create proofs, create verifying module, create verifier, and then it usually have like modules. You can integrate these modules with like, JavaScript or Solidity or with different like other programming languages and platforms. So for more like for the core algorithmic considerations, there are like many different ZK or SNARK or similar, not necessarily even SNARK, but similar structures from a cryptographic point of view. Again, all of these things work in a way that we have a prover, we have a verifier, and the prover tries to prove something in a way that the verifier gonna trust or non-trust, and there might be some parameters hidden, and this proof is basically small and easy to verify. Again, we have like more strict definitions in SNARK, not so strict definition with STARKs, but basically that's the main idea. As we saw in the last 3 sessions, there are many ways of like building even a SNARK. So we can use like different polynomial commitments and different interactive oracle proofs, and then we can create like many different SNARKs. And there are even structures that are not really SNARKs, but something similar like STARKs. That's a scalable transparent argument of knowledge, for instance. But from a general point of view, what's interesting is that, I mean, these core algorithms have like on a high level different characteristics, and that's actually what we need. So for a very, very simple comparison, what we are having a proof size, we have verification time, we have a setup, and we have like post-quantum properties. So what we would expect that the proof size should be small. I mean, especially if we consider like blockchain applications. I mean, yeah, I mean, in blockchain, you know, every byte counts, or every bit counts, actually. So we don't really want to write many information into the blockchain. So the size of the proof should be as small as possible in blockchain applications. So you can see, for instance, in STARK, like with 100 kilobyte proof, you don't want to write into the blockchain. So you might as well use like for applications that are somehow integrated with the blockchain, but it's like just based on the proof size, it's not something that you necessarily write into the blockchain. But again, that's like proof size. The second property is verification time. I mean, verification time matters, of course, because if we want to like verify things on chain, we usually have a smart contract that takes time and usually, you know, like a transaction fee or gas fee to run. And then we just want to fit into the block time as well. So verification time is critical if we want to verify things in the blockchain. So like if you take a look like row 16, that's pretty fast. Plonk Merlin is not so fast. Bulletproof is pretty slow, and again STARK is fast again. So that's a property. Usually we don't consider very strongly, but that's the verification time. Actually, the proof, creating the proof time, I mean the time of creating the proof, that matters as well. So I mean, in sometimes, or I mean, creating the proof might be like even minutes and sometimes even hours. But you know, if in a large problem, like the proof creation time is like days or weeks, that might not be accepted in most of the applications. So again, proof time or proving time is not so critical, but it matters as well. And we can have many different setups. We can have like one setup for each circuit. We can have like a universal setup, and we can have something which is a transparent setup as well. And we can have like post-quantum properties as well. I mean, post-quantum readiness is getting to be a more and more critical topic. So it's a question, if we create something, we just go live with an application which is not post-quantum ready, and then, you know, I mean, that's blockchain. So all of this data is written into the ledger. And what happens actually if we get like, you know, fast enough quantum computers, like in, I don't know, 8 years, we would still need to use this application, this blockchain. And again, like the old proofs are written into the ledger. So the question is if that use case is manageable. And based on these properties, we have like, you know, typical setups is like row 16, which is fast, small proof size, fast to verify. Unfortunately, it requires a trusted setup per circuit. and it's not post-quantum ready. We can have like Marlin, Plonk, and Marlin, which is like a bigger proof size. It's just slower to verify, and it needs like one centralized universal setup, but it's not a setup per circuit. It's just one universal setup, and it's not post-quantum ready. We have like bulletproof, which is having like a big proof size. It's pretty slow to verify, but it doesn't need like a trusted setup. It's transparent setup, but it's not post-quantum ready. And we have like STARK, where the proof size of the proof is extremely big. The verification time is somehow average. It needs a transparent setup, and it's already post-quantum ready. Actually, there's no perfect solution for each and every problem. We just need to, or application, we just need to pick like, the adequate algorithm. And then, of course, one of the biggest question is, I mean, if you have like certain tools, then only few of these core algorithms are practically supported. So, for instance, in circum, we can use like row 16 and Plonk and Marlin, and neither of these gonna be like post-quantum ready. So, and again, one more consideration. We can have like many different platforms, and then if you just want to pick a platform, then there are some practical considerations as well. So first, there's like the language, like Noir, Circum, Leo, Cairo. So there are languages which are like self-defined domain-specific languages, like Circum, but there are languages which are like more like Rust-based languages. So if you are familiar with Rust, then you might as well prefer something which is like Noir practically. Then very practical considerations is like the integration what the platform supports. So if you have like JavaScript modules, then you just and you have like JavaScript or Node.js development anyway, then you would pick like a framework that supports very well like Node.js frameworks. If you want to integrate with like Rust, then you probably pick just Rust-based language and framework, for instance. Again, it's like a very, very practical consideration. So having Circum, Circum is basically a domain-specific language and a full platform, a full toolkit practically. What we have is a circuit programming language and the development environment for arithmetic circuits and constraints. It was used, for instance, in the famous or unfamous Tornado Cache application. It supports Grow 16 and Plonk as core arithmetic operation. It is pretty well established. It exists more than actually 4 years, I would say. This is like an old slide. And it has like pretty good integration with like JavaScript, SNARK.js, which like C++, and it has like a solidity verifier as well. So this is like a high-level structure of Circum. There's like a high-level circuit description. There's a compiler which compiles this high-level circuit description into something which is low-level circuit description, or it's actually not just circuit description, but like rank 1 constraints. Then we can have like a trusted setup. Basically, I mean, depending if you use like Grow 16 or Plonk. In Grow 16, we have like trusted setup for each and every circuit. In Plonk, we can have just one trusted setup. I mean, generally, the problem is the trusting setup that, I mean, if your trusted setup is compromised, that, practically the one who has your trusted setup or keys of your trusted setup can fake practically proofs. So you just need to take care practically that your trusted setup is not compromised, is not, modified or copied or practically compromised by a hacker. Then we get some proving keys and validation keys, and then we can have like, I just forgot to mention, basically, we start with the high-level circuit description, but the high-level circuit description is our problem that we want to express. So as soon as we have it, we can have like our inputs. It's going to be like public and private inputs, and based on the proving keys and public and private inputs, and again, based on the compiled circuit, which is our problem description, and based on the setup, we can create like a zero-knowledge proof. That's going to be this proof pi. And we have this validation key practically. And then basically we can, based on this validation key and proof pi, we can just validate basically our proof. And it's going to be either accepted or non-accepted. So that's like the whole flow for circum. So let me just show you a demo. And then basically, you're gonna find the demo if you go to GitHub. Again, this is my GitHub. It's gonna be on the slides, but basically that will be migrated to a Linux Foundation Decentralized Trust lab. And then basically what we have here resources for each and every meetups. We have like the slideshow, the recording, sorry, that's the syllabus, like links and literatures, sometimes quiz, even the link to the meetup. And then to this point, we did not have like code example, but if you take a look on this one, then we have code. And the code is checked in here as well. So if you just go to circum basic, that's what we're gonna cover now as an example. Okay. So basically, if you just clone this repo, then you will find the basic example, the circum basic example that I'm gonna demonstrate again at the moment. So if you just copy this or clone this repo, what I'm having here is like, we just have like the circum basis. And what we have here is a demo1.circum. It looks that way, that basically if we program, so let me put it that way, circum is pretty much low level. What we do, we just define circuits, arithmetic circuits in a way. So a circuit is practically a module. This is like a circuit. We just gonna create some inputs. We just gonna create directly inputs and outputs. And we have like two different inputs eventually. One gonna be like a private input and the other one gonna be like a public input. Okay, this is like an output. And what we have here, we just create here practically rank 1 constraints, which is like, I will just show in a second. And this is like a module. And what we say here, that these are basically signals. And eventually how we build up our application is that we just create these circuits. And then basically we have like another circuit, which again have some logic here. And then we have some output here. And what we do is that we just wire these signals. Okay. So this is like another output. So we can have like another module. And then basically, this is some logic. It has some inputs again. It has some outputs. And again, these are like signals, and we can just wire them practically. And that's how we build up our application. Again, you can say it's pretty low level. That's right. It's pretty low level. So it's like not exactly directly programming like arithmetic circuits, but it's pretty close. But I mean, perhaps just taking a look at the first zero-knowledge programming application, circum is a good start because, I mean, we see almost pretty close what we program in a way. We are pretty close to the to the original definition of the arithmetic circuits, which is like the core component of zero knowledge programming. So in a sense, even if it's low level, I would say it's a good start for learning zero knowledge programming. On the other hand, what's probably more important, this is very efficient. So we have like a lot of higher level languages. You can imagine that if you have like a real procedure or object-oriented language, and that you want to compile somehow eventually to like arithmetic circuits or to lower level polynomial structures, that can be very, very inefficient. If you program directly like arithmetic circuits, of course, it's pretty challenging. And as a developer perspective, it's probably not much fun, but it can be very, very efficient. So the way we start is that this demo1.circum, we have like one template, and then basically it starts with template. It's a demo1 template. A template is practically a possible circuit that you can initiate several times. So this template demo1 is basically a possible circuit. It has some inputs. Again, these are like signals. We can have variables as well. It's something that I will demonstrate in the next session. But generally, what we develop here is kind of circuits. So we have like signals, and these are like input signals. We have like a signal input A, and we have like a signal input expected cube. So these are like two input signals. And we have like an internal signal as well. An internal signal is just somewhere here, basically. Okay. So it doesn't have like input or output. And we're going to have like one output that's practically cube. So again, this is like the structure of our circuit. And we're going to have like some constraints. It says, so we can have generic constraints and calculations. But what we want to do is to do some calculation, some constraints eventually. So what we say is that A times A, and A is this input signal, should be this internal signal, which is calc, and A times calc should be the cube, which is like the output signal. And we have like one more constraint that practically expected cube equals cube. Okay, so what we say here that basically these two inputs, A times A equals the expected Q. So basically, this circuit represents somehow a cube of an input parameter A, and practically, I mean, that's the basic parameter, and we have like the expected cube, and A times A should be equal to the expected cube. Okay, this is just a general template. So we can use this general template in like initiating several times. We can build up like, some more complex circuits, or use as practically as a module or part of our program. But we just keep it simple, so we don't use it more than one time. We just initiate it once. We have like this component main expression, and then we just initiate it once. So there's gonna be just one circuit based on this demo1 constraint. And what's more important, we can define at initialization which are the public parameters and which are the non-public parameters. So at this moment, we just have like one public parameter, which is like the expected cube. And again, we have two input parameters, A and expected cube. And that's basically expected cube is like the only public parameter. What we define here is a logic that we know an input A, which is like like if we have like this A times A, that's gonna be the expected cube. and the expected use is public, but we just keep this practically private. So it's something that we know like a cube root of an expected cube without explicitly saying what's this cube root practically, which is like a. Okay, so that's the general idea, and that's actually the program. We've seen everything from the program itself. So let's see how we can run it and verify. And for this, what I'm having here, I have just one run bash script, which basically do a lot of things. I will just run it. I will cover a few things practically, but it just setups and creates everything. So first, what I'm just gonna compile this this high level language. Again, this is like, I mean, this is itself the high level language. You can challenge me if it's not so high level anyway, but basically we just gonna compile it to a more lower level representation. So we're just gonna compile it for the first one, again with circum. Then we just copy a few files. There's gonna be like basically a subdirectory called demo1.js, and we just copy everything there practically. And then we just gonna generate witness, but what's more important practically, we're gonna have this so-called power of tau setup. Power of tau setup is basically the setup for the proof itself. So if I just go back to this slide, there's like a trusted setup. And the trusted setup looks that way, that there are some secrets that should be generated. And even this secret generation can be more decentralized. And even if it's like theoretically a centralized secret generation, we can just execute it in a more decentralized way. And that's what we call as a power of tau setup. And what we're gonna have here is a power of setup with two phases. So two phases of this power of setup practically means that that this random setup can only be cheated if both of these phases cheat. So practically what we have here usually, even if like a trusted setup, we have like two or more phases, and if any of which are practically executed by different people, and if any of these different people are honest, then basically we're gonna have like more or less a trustless setup, which is of course a trusted setup, but with the help of this power of tau ceremony, it was created more trustless. So at the end, we have like we have one verification here. It doesn't matter. Some random, some power of tau finish, and what we're gonna have here, based on this power of setup, we just set up practically Plonk. We can use here Plonk, or we can use here grow 16. So again, it's with like the SNARK JS commands, and then we can have like the verification key, and we can use the command prompt to create a Plonk proof, and basically we can even verify this this proof with like the verify proof. Anyway, if you just go to README, you should find more of this information somewhere here. Yeah, this one. So basically, if you just want to run this setup, first you need to install circum. But I just put like a link how you can install circum. You just need to install Rust and then basically circum. And to compile and generate proofs, we just run this run bash script. So let me just take a look and then run this basic. And I'm just gonna run .sh. So it's gonna take a little time. again, this is like a power of tau setup, and then I'm just one of the person creating this power of tau setup. So I just put some entropy in, basically. It's like a little bit, it's just taking like 2 minutes. There's like a fast Fourier transformation in it, which takes time, unfortunately. It depends a little bit on the size of the circuit as well. So if you have like big circuits, then this power of tau might take like, even hours. But at the moment, it's just, I would say it's probably like 2 or 3 minutes. So let's see if it ends. But I mean, generally, it looks that way. I'm not quite sure. One of the blockchains that use like zero knowledge proofs with a trusted setup use like this power of tau ceremony with like 1,000 people. And again, it looked that way, that it was like one secret at the end. But basically, as this secret was generated by thousand people that were supposed to be like independent from each other, basically, if even if like one person from this 1,000 were not cheating, so were created like really really a random number to this ceremony, then the result was practically without problem, without like the possibility of being cheated. So it's just taking a little bit. So theoretically, that's the end. So we just have everything. And then at the end, we even like created like a test proof, and we created like a test verification as well. Again, with the common prof. So for instance, our proof looks that way. So this is like, this is a zero knowledge proof after, so much.
Daniel, looks like you're muted, by the way. The sound went off.
Yeah, sorry. So basically at the end, we just created one zero knowledge proof. So let me just take a look if I can somehow demonstrate it. It just doesn't load for some reason, but huh? So just give me a sec, and basically this is somewhere our zero knowledge proof. I'm not quite sure if I can. So I'm just looking like a JSON visualizer. But basically, after so much struggle, this is the same one. Yeah, that looks great. So view, yeah. So that's what I was looking for. So that's our zero knowledge proof at the end. Voila. I don't know if I'm not sure if I know each and every detail. It's like, that's like a cryptographic proof, but that's what we generated basically. And eventually at the end, we just have one prompt which takes like the verification key, some public parameters. So these are like the public parameters. It's like the public JSON. I think that's like, so that's the proof. That's like the, it's probably somewhere here. So again, we have like two inputs. We have like the input JSON, which we use at the generation, which uses like A, which is 99 at this example, and the expected cube is like this pretty big number. So that's what we have, and we have somewhere a public JSON, and public JSON is just this 907,299. It's just a trick that we use it like 2 times, but eventually at the creation of the proof or at the verification of the proof, we just use this public information. So practically we prove that we know a cube root of this number without practically knowing what's the cube root. So that's the trick. And some more things that we have here. Let me just go back to the README file. So what we can do, we can just create a proof and the verification with Node.js. It's again, it has a Node.js package. I just integrated it a little bit with some Node package manager, but we can create a proof again, this time with like a Node package, a Node.js package. Again, that's like the same cryptic thing. We have here the public script signals, and then basically I can even verify, and then the verify looks pretty similar, which is like, again, it's nothing special. It says true, so it was successfully verified. And one more thing, we can generate actually a Solidity smart contract as well. And the Solidity smart contract gonna act as a verifier. So practically what we are having here is that we should have here somewhere under the demo1.js a Solidity code, which is verifier.sol. So that's practically a smart contract that can act as a verifier. So if I just put into my Solidity code, then basically it's like an automatic Solidity automatically generated Solidity code. These things has changed already like a few times. So perhaps I don't even start like Remix, I don't fight with it, but if we just put this code to like any kind of Solidity development, it creates like a verification. It has somewhere one function which is verify proof, and then we are having like one more function which is like practically creating a call. It's a help function as well, creating a call to this smart contract, to this Solidity smart contract. That's like an example call, and then basically it starts basically just having the proof and then giving this proof to the Solidity verifier, and then that's going to be our proof. And then the public input should be actually here as well, and based on the proof and public input, the Solidity code gonna verify our proof practically, and public input. So again, that's basically the same. It's just a call to the Solidity smart contract. I think this is gonna be the proof that we generated, and this is gonna be like the public input. That's like this 700,000, and then we can just verify even with the Solidity smart code that we know a cube root of this pretty big number, which again somehow looks that way. So this one is the public input. Okay, so that's the code. You will find everything. So basically, if you go to circum basics, and just take a look on README. You will find all the setups, basically, even with like circum installation. So that was the demo. Again, we have a template for arithmetic circuits, public input, private inputs, outputs. Practically, we create rank 1 constraints and calculations. We have like a setup which is power of tau. We just create a proof of certain inputs, and we have verification for JavaScript and Solidity. So basically, that was the content for today. I have one developer challenge. If you're interested, it's very basic. So if you want to try out like circum, then the challenge is that create a proof. It should be like a Fibonacci-like series. I say Fibonacci-like series. It shouldn't necessarily start with like 1, 2. You just start with any two numbers, your Fibonacci series, and then you should just prove that the kind of an output is the 10th series of a Fibonacci-like series of two hidden private starting elements. So again, you just start somehow with like two numbers that should be like private input, and then eventually prove it that it's like you have like one output which is the 10th element of any two hidden private input, and it's gonna be the calculation of like a Fibonacci series. Again, it's not fully Fibonacci because you just don't start with 1 and 2, but like with two hidden inputs. And I'm having some links and literatures at the end. You will find like links for tutorials. You will find one Circum workshop link here. You will find a repo for Circum, install Circum, Circum documentation, and then basically you will find actually my GitHub repo for zero-knowledge learning and for this demonstration on the first slides. So that was all for today. Well, actually, we are having just 1 minute. So I would say we can have like one very small question. Otherwise, I would just encourage everybody to use basically the chat from Linux Foundation Decentralized Trust, and then just have your question here. So I mean, let me just browse the chat basically if you have like any questions. Yeah, like what's the point of having it's like the calculation, I guess. So I mean, the calculation is like, that's like your domain logic basically, that you want to express in a way. The recording will be published basically, and then, well, I mean, I would say that was all for today. Again, it was taking a little bit longer. Next time we just go more in depth into Circum, into different programming features of Circum. So we just try to have like more time to answer questions. So thank you very much for your time, and well, I would say see you next month in the next Circum programming session.
Great. Well, thanks, Daniel. Thanks, everyone.